Hello everyone, welcome to this lecture on electrical measurements. So in this topic we are going to see the principles of measurements. So under this we are going to see the basic requirements and of the indicating instruments and the principle of an indicating instruments and what are the things behind the control and damping devices and what is moving coil instruments. Before going to the basic requirements of the indicating instrument or the measuring instrument, so we need to know why we need these instruments. Okay. So basically in the recent days or recent years we are using the electrical appliances a lot more. So using the instruments safely we need to measure the voltage and the current values. Okay. So for that, see we have to measure either voltage or the power or the current value. So what we are going to do, we need some instrument to measure these values. So how we are going to measure these values? By means of making some arrangements. That arrangement we are going to discuss today. Okay. For that we need some requirements to make the measuring instruments. What are the requirements we need? So in this diagram itself I mentioned a pointer, a moving system and a scale. Okay, so we need the pointer. Okay, this is the pointer actually and this is the scale. So this is the pointer and this is the scale and this is the U-shaped magnet and this is the armature. Okay, so these things we need to make the indicating instrument. The next thing is the pointer associated with the moving system of the instrument and it moves along the movement of the moving system. So in this diagram I am mentioning this is the pointer actually. This pointer is attached here with this is the moving armature. So entirely we are saying that this is the moving system. So in this moving system the pointer moves along with the moving system on the scale. From this you can find the value of the measurement value which you are going to measure the quantity. Either it may be a voltage or it may be a current. Okay. Then during the measurements, after completion of the measurement, the pointer rests towards the specific point in the scale and dial include the measured value of the quantity. So according to the value of current which I am giving to this coil. Okay. So first of all, before going in deep to the principle of operation, we should know the Faraday law of electromagnetic induction. Okay. Suppose I am having the current carrying conductor. In this conductor, if I pass the current to the current carrying conductor, the flux will be created around the conductor. Okay. Suppose this is the conductor means, suppose I am having the conductor like this. If I pass the small amount of DC current around the conductor, we feel some fluxes around the conductor. By means of the experiment, we can analyze whether it will create or not. But actually it will create. That's the Faraday's law says. On that principle we are going to use in this measuring instruments. Suppose I am passing the current through the conductor, it will create the flux. That flux reacts or give any sort of force or any sort of movement in the coil. Okay, like that we are going to use here. So for the movement of the pointer, so I have to move the pointer along the scale when I am giving the current or I am giving the energy, some energy to the coil, it should move along the scale. So some necessary things we need to move the pointer along the scale. What are the things? The first one is the deflecting torque. And the second one is the controlling torque, and the third one is the damping torque. So what is deflecting torque, what is controlling torque, and what is damping torque? We will see one by one. The first one is the deflecting torque. What is deflecting torque actually? The torque is nothing but a twisting moment. Suppose initially any object is in the rest position, we have to move the object from one point to another point. For that we need some force. For that force, we can say that is the torque. Suppose I am giving the high torque to that particular object, it will move rapidly, and if I give this low amount of torque, and it will move slowly. So according to the input given to that object and according to the torque produced, the system will operate like that. The deflecting torque is produced in the moving system here. This deflecting torque may be created by some sort of means, that is by means of magnetic effect. Here this is the magnetic effect, electrostatic effect, and electrodynamic effect, thermal effect, and the inductive effect. So these things are well familiar. Magnetic effect in the sense, already I am said that if I am passing the current, it will create some magnetic flux. In that magnetic flux, suppose I am inserting some object, it will react, it will act accordingly, according to the magnetic effect present in the nearby conductor. Electrostatic effect means based on the charge, positive charge. Suppose any atoms made up of positive charge or negative charge, we can make it accordingly. By the doping, we can make either it is a positive charge and the negative charge. Suppose the positive charge attracted by the negative charge, in the sense the movement is happening. Like that, the electrostatic effect will work on some set of instruments. Then electrodynamic in the sense, it's like a motor. Suppose I am passing the current, by means of that current the movement is taking means it is the electrodynamic effect. Thermal effect is nothing but due to the temperature variation. Suppose an EMF will be produced means based on that EMF the flux will be produced. On that we can move the coil or an object. And in the likewise the inductive effect also in the same way by means of the induction principle. So nearby coil the flux is linked means the coil will react accordingly. So by means of these effects the deflecting torque will be produced on the indicating instruments. Once the deflecting torque is produced means the pointer starts move from its rest position to the desired position, which quantity I have given to the coil. So based on that the movement is happened according to the deflecting torque is produced. The next the point is discussed what I am saying previously. Then we need the controlling torque. Okay, so once the deflecting torque is produced, the point is moved along with the scale without any disturbance until I give the supply. So I will give the supply keep on means the pointer moves without any disturbance. But I have to stop somewhere else to measure the quantity. In the 180 degree position only I have to make the scale. See in this diagram here I made the scale by the 180 degree. Suppose I am keep on giving the supply to the coil, means it will rotate further. It will not happen. Somewhere I have to control this rotation and to stop the pointer at some position to measure the measuring quantity. For that we need some controlling torque. Controlling torque is nothing but some opposite torque to the deflecting torque. Suppose one object is moving in this way, I have to stop this object, means I have to give some opposite force to this object. So this is the deflecting torque means, and this is the controlling torque. So by means of the controlling torque, I have to stop the deflecting torque. So by means of this condition, this means I can control the deflecting torque. In turn, I can control the movement of the pointer, and it will rest at some point which we are going to measure the quantity. Like that, the controlling torque is working. So here also I am giving some points to this controlling torque. So we often refer the controlling torque is the restoring torque. So the another name of the controlling torque is nothing but the restoring torque. Why we are calling it is the restoring torque? We have to set the pointer to the desired position. Suppose the one movement is happening. By means of giving the current to the coil, one movement is happening. I have to stop. Suddenly I stop that particular movement action. It will not stop at the instant. It will oscillate here and there, like that. Here and there it will oscillate. At some sort of time, it will rest at some position. That is the actual measured value. But it will take some time. It may take some time to restore. The deflecting torque applied to the moving system is equal to the all position of the dial scale. So I have to control the deflecting torque value. I have to give the equal amount of value. Okay, suppose I am giving it will some torque is created actually, that the deflecting torque is created actually based on the deflecting torque only. The pointer is moving along the scale. I have to stop the pointer. So which amount is the deflecting torque is created, the same amount of the opposite torque, that is the controlling torque is given only, means it will stop the pointer to the desired position. Like that they are saying this second point. Then the third one is the deflecting torque and the controlling torque act opposite each other. That I discussed already. That the point is here. The next one is the amount of deflecting torque only depends upon the strength of the measuring quantity. So always we can say that the amount of deflecting torque, so based on the current or voltage which I am giving to the coil, that set moving setup, it will react accordingly. Beyond that we can't move further, we can't do anything, we can move further in the coil. So in order to stop the pointer to the desired position, we need the controlling torque. So we need to apply some external force or external voltage to that particular system. I can stop the. So here how we are going to control how we are going to generate the controlling torque here in this system, that we are going to see further. So this is one example of creating the controlling torque. There is a spring control. Okay, there is a spring control. So in the spring control, the spring connected measuring instrument, we attach the phosphor bronze hairspring. Phosphor bronze hairspring. So see in this diagram mentioned, this is the phosphor bronze hairspring. So the top and bottom we are having the pass per bronze hairspring. So this spring is actually tightened when the moving system is moved from the rest position to the desired measured quantity position. Once I am releasing the supply to the measuring system, okay, when I am releasing the supply to the measuring system, it will automatically get back to that original position by means of the force acting on the hairspring. So by means of the spring control, we are control the movement of the pointer. Okay, so by means of this, we can control the oscillation, the timing of oscillation. Before that, we are giving the deflecting torque to the instrument. It will move the scale, and actually the point is moving along the scale, and I have to stop at the one position. I have to give the controlling torque. Even though I am giving the controlling torque, it will not set at the instant. It will oscillate here and there. At the particular time, at the instant, I have to stop the pointer to that desired value. Means I have to give some control. Okay, that control is based on the hairspring. Suppose the tighten of the spring is more, means it will come the rest position by the small amount of time. Okay, based on that we can work on it. And another way we can give the controlling torque by means of the gravity. So by means of the gravity control, I can give the controlling torque. So we achieve the gravity control by attaching adjustable weight on the pointer, tail of the pointer. Okay, so on the tail of the pointer we are going to attach some weight. Means based on the weight we can give some controlling torque. Why we are giving the controlling torque? Actually you have to control the deflecting torque. Okay, so in order to set right the pointer at the desired position within a short amount of time, you have to centrate the point in the desired position. That's why we are giving the control signal or controlling torque to the particular instrument. So in the gravity control, that torque is directly proportional to the sine of the angle of the pointer. So if the pointer is moving along from 0 to the 45 degree, that sine 45 degree gives the torque value of the gravity control. Okay, like that I am mentioning T is directly proportional to the sine theta value. The next is the controlling torque is minimum when the pointer of its zero position. Okay, so normally we can say that actually the pointer is in the rest position. Okay, actually the pointer is the rest position. There is no deflecting torque. If there is no deflecting torque, means we don't need any the controlling torque. So the controlling torque is minimum when the pointer is at the zero position, and it is maximum. Which one? The controlling torque is maximum when the pointer goes to the 90 degree deflection. Okay, so the pointer is from 0 degree to the 90 degree position, the controlling torque should be maximum. If it is maximum only, we can control the deflection of that particular pointer. So I have to control, or I have to set right the pointer in the particular position. That's the main thing, that's the main aim. This is the reason for which the scale of a gravity control instrument is not uniform. Okay, so this is the main disadvantage of the gravity control measuring instrument. So this point is given for the gravity control disadvantage purpose, because the weight of the gravity, the weight is not uniformly distributed along the scale, because the controlling one set of point is controlling torque is minimum, and the another set of point the controlling torque will be maximum. It should be maximum. By means of the gravity control, it will not attain, like that I have said. Then there is the another major disadvantage of the gravity control. What is the another major disadvantage? The measuring instrument, and it is that the instrument is always keep in the vertical position. So for the gravity control, based on that weight only, the controlling torque is produced. If I keep the gravity along with the z-axis, x-axis means actually it should be in the y-axis. If I am saying in the graphical way, it should be in the y-axis, gravity weight. If I am placed in a horizontal position, that is the gravity in the x-axis, it will not give any controlling torque to the measuring instrument. That is a major disadvantage when you are giving the controlling torque by means of the gravity control. That is the main point. This is actually the gravity control. This is the actual picture. So I have to. So this is the actual picture. Okay, this is the gravity control, and this is the scale. So by means of this balanced weight, the controlling torque will be produced through this pointer. Then the damping torque. So already I said that for the making the measuring instrument, we need three different kind of torque for the moving system. One is deflecting torque, another one is controlling torque, and the third one is the damping torque. So here the damping torque. What is damping torque actually? So far we come to know that deflecting torque deflects the moving system or the pointer in the instrument. The controlling torque helps the moving system to stop the desired position during the movement. When the pointer comes to the desired position, it may oscillate. So here and there. So it will not come at the instant. It will oscillate here and there for some sort of time. I have to stop at the instant. I want to stop at the instant, or a small amount of time. I have to stop the pointer. I need to give some damping torque. What is damping torque and how we are going to give the damping torque? We are going to see one by one. So there are damping force opposes the momentary motion of the moving system. Okay, the damping force opposes the momentary motion of the moving system. What is a momentary motion? Actually, the oscillation. Due to the deflecting torque, the pointer is moves from the initial position to the desired position. By means of the controlling torque, I can stop the pointer at some sort of point, but it will not come to that particular point. It will oscillate here and there. That oscillation is nothing but the momentary motion here. So I have to stop that momentary motion by means of this damping force. So sometimes the underdamped system, underdamped in the sense we are not giving any sort of force to that controlling torque to set the pointer to the desired position at the instant. That is called the underdamped system. Suppose I am giving the over damping to the system, that two systems give the readings in a very delayed manner. Okay, we will not measure the quantity at the earliest. We could not measure the quantity at the earliest. It will give some delay to the measured value. So correct damping only gives the correct control both for the deflecting as well as the controlling torque. So what type of dampings we are having? First one is the air friction damping and fluid friction damping and eddy current damping. So these are the three types of damping we are having to give the damping force to that existing moving system that already having the controlling and the deflecting torque. So this is a picture of the air friction damping. So this is the air chamber. This is the air chamber and this is the pointer actually. Suppose the pointer is moving along this direction, and I have to stop the pointer to this desired position at the earliest possible. So by means of controlling torque, I can stop the pointer to oppose the deflecting torque, but I have to set right to the minimum time period. I have to give the damping force to that particular shaft. So this is by means of the air friction. Okay, so in this chamber we are having the air. By means of that, I can give the force to that particular moving system. Based on that, it will stop at the minimum sort of time. Okay, so these are the two mechanisms we are using for the air friction damping. So in the air friction damping, the lightweight piston moves along a cylinder filled with the air. Okay, filled with the air by using the vane. Sometimes we are using the vane moves in the free air. So the second diagram depicts the vane moving with the free air. Like that we are giving the damping force. Or in the air chamber, a piston is moving along in the cylinder. In that way also we are giving the damping force to the moving system. So two type of air friction dampings we are mentioning here. A vane is moving along with the free air, or a piston moving in the cylinder which is filled with the air. So what is fluid friction damping? So in the fluid friction damping, a piston moves with the movement of the pointer inside the cylinder filled with the oil. So previously we are said that in the air friction damping, the air is filled in the chamber. So instead of air, if I am filled the oil, then I can say that is the fluid friction damping. So what is the difference between this air friction damping and the fluid friction damping? So in the fluid, if I fill the oil in the chamber, the weight of the instrument may increase, and suppose if any breakage in that chamber, the leakage may occur to cause not produce the correct damping force to the moving system. That is the major two disadvantages in the fluid friction damping. So the weight of the instrument is, that is the main point, weight of the instrument is heavier and the air friction damping of the instrument than the. So the next one is the eddy current damping. So what is eddy current actually? Suppose if the magnet is present, some aluminum disc is moving along the permanent magnet, it will create some eddy current. It will create some opposite force to the main field. It will give some opposite force to the main field. So based on this force, I can give some damping effect to that moving system of the instrument. Okay, so I will show the diagram that it will understand easily. So this is actually the eddy current damping. So by means of the spring, this hair spring, we are giving the controlling torque. When I am giving the current to the coil, it will give the deflecting torque, and by means of this disc arrangement and this U-shaped magnet, I am producing the eddy current in the disc. This eddy current produces some sort of a current that will oppose the main field current, that will give the damping force to that particular moving system. Okay, so in this way we can give some eddy current damping to the system. Then moving coil instrument. So now we have discussed what are the things we need for that indicating instrument. What are the things we need first? Moving system, a pointer on the scale. So based on that instrument, I have to create some deflecting torque. Based on the deflecting torque, a pointer is moving along the scale. Then I have to stop the pointer. For that I need the controlling torque. Even though I am giving the controlling torque, the pointer will not set right at the desired position for the small amount of time. I have to set the pointer for the small amount of time. At the small amount of time, I have to give additionally to the damping torque. So based on that, the instrument is working. From the construction and the principle point of view, I can create the moving coil instrument. Okay, so there are two types of moving coil instrument. One is permanent magnet moving coil instrument and the dynamometer type instrument. Okay, we will see one by one. So the working, now we are going to see the permanent magnet type moving coil instrument. So what is permanent? The name itself says that the permanent magnet moving coil. So anyhow, the coil is moving along with the magnetic effect. So due to the magnetic effect only, the coil is moving. Based on the coil movement only, the pointer is moving on along the scale by means of creating the deflecting torque. So here also giving the same point, the working principle of the magnet, that is permanent magnet moving coil instrument. So in this type of instrument, we allow one coil to move inside a magnetic field. Okay, only one coil I have to insert the magnetic field whenever we place a current carrying conductor inside the magnetic field. Suppose this is the permanent magnet. In the permanent magnet, this is the north pole and this is the south pole. So between the north pole and south pole, we are having so much amount of flux or flux density in this gap, north pole and the south pole phase gap. So in between gap, I am inserting a magnetic coil, that is coil, that current carrying conductor. Suppose I am going to insert, means it will create some movement. It will create some movement. That's the thing we have discussed here. So there is a mechanical force acting on it. So in the coil, there is a mechanical force acting on it based on the magnetic flux produced in the permanent magnet. So actually the magnetic flux produced in the permanent magnet is constant, and actually I have to give some current to the coil. So based on the current and the actual flux produced by the permanent magnet, between these two and interacting these two only, the moment moment force is created on the coil. Okay, moment force is created on the coil. So depending upon this principle, we construct the permanent magnet moving coil instrument. On the construction point of view, as the name suggests, there must be a permanent magnet. Already I said that there should be a permanent magnet, and we allow the rotating at very lightweight coil. So we have to use one lightweight coil in the rotating frame, armature frame. So it will have so many thin turns. Okay, so in order to make the lightweight coil, thin turns we need. Okay, so it will turn around the aluminium frame inside the magnetic field. So created by two poles of the permanent magnet. So this frame creates the two poles of the permanent magnet inside the permanent magnet. So when the current flows through the coil, there will be a mechanical force acting on the coil. That's the actual thing it is happening. Okay. So this is due to the interaction of the current with the magnetic field. Okay. So this mechanical force acts on the deflecting force, that is creates the deflecting force of the instrument. So we use the Alnico made U-shaped permanent magnet. So for the permanent magnet we are using the Alnico material that is formed by U-shape. So the curved hole faces provide a cylindrical space between the coil. Okay, actually we are having some curved hole. Here it is. Here it is. We are having the curved hole. Okay, normally it will not in a flat surface. If it is a flat surface, means the flux distribution will not be uniform. So the flux distribution between the north pole and the south pole will not be uniform. Since this is the rotating armature, you have to give the uniform flux density or fluxes between the poles. That's why I am giving some curved nature of this permanent magnet. This is the U-shaped magnet. We can see it clearly in this diagram. This is the north pole and the south pole, and this is the curved shaped magnet. In order to rotate the cylinder aluminium frame. And this is the iron core we are having. So between the core we are going to insert this iron core, cylindrical iron core. On that cylindrical iron core we are having the aluminium frame. On the aluminium frame we are having the number of thin turns of the coil. So in this coil only we are going to give some amount of current. That current is going to be measured by means of the moment of this armature. Then the next thing is we are going to attach two phosphor branch hairspring in order to give the controlling torque. So we will see one by one. First the permanent magnet and the cylindrical core. On the cylindrical core we are having the aluminium frame. On the aluminium frame we are having the number of turns of the coil. The lead is turned outside to give the supply to that coil. On the shaft we are having at the end, top, both bottom and top, we are having the hairspring. And on that we are having the scale. This is the scale actually, and we are having the pointer. So suppose I am giving some supply to the coil. Based on that supply, the armature, that is the cylindrical part, will rotate. This permanent magnet already gives the fluxes value, and this current gives some sort of fluxes. By interacting these fluxes, the moment is taken by means of creating the deflecting torque. This shaft is already connected to the pointer on the scale, and it will move along with the shaft and give the point to the user. So here we are having some advantages and the disadvantages of the moving coil instrument. So we are going to use the moving coil instrument. So this instrument consumes very low power because of the light weighted coil. So this is the main thing we should know. Suppose I am going to use the instrument to that power system or the circuit. It will, suppose it drops more amount of power, it will drop more amount of voltage, means not necessary to connect this device to that electrical circuit. Why means it will losses the heavy amount of power from the supply, means we can't use the power what we are created already in the generator. Suppose I am in the generator, I am created or generated 440 volt supply. Suppose for example I am saying 440 volt AC supply. That 440 volt AC supply, the 40 volt is dropped in that instrument, means suppose the coil is having more resistance value. Okay, that meter coil is having the more resistance value, it will drop more amount of voltage. So the more amount of voltage is dropped means no need to use that instrument to the power system, because it is actually wasting the voltage which we are generated in the generator. So at the end of that meter we are having only the 400 amount of volt, 400 volt only. So that's the main thing we should know. It will consume very low amount of power. It will consume only the low amount of power. Then what is the next thing? The angle of deflection of the pointer is directly proportional to the current. That is the main thing. If I am giving to the current to the coil, accordingly it will work. Then only I should know which amount of value I can give to the coil. It will move proportionally means I can control, or I can damp, or I can create the deflecting torque. It's very easy. So the parameter is directly proportional in this case if you are using the permanent magnet moving coil. Then the instrument produces very high torque compared to the weighted moving system. Okay, so the instrument produces very high torque compared to the weight of the moving system. Okay, the weight of the moving system may change, but whatever may be the condition, the torque will be very high. As there is no magnetization or demagnetization of the iron during the operation. What is magnetization and demagnetization means? Suppose this is actually the coil. If I am giving the positive point to that left side and the negative point to the right side, there is no problem. It will magnetizing, keep on magnetizing till the saturation occurs. If I reverse the power to the coil, it will create the demagnetization effect. Actually, due to the positive and the negative point, the coil is already magnetizing. If I am giving the reversal of supply, it will make some demagnetization effect. That will not happen in this coil, since we are giving only the DC supply to the coil. So the magnetic effect is permanent, it is static one. Then the aluminium frame used for handling the coil provides eddy current damping. So in nature I got to create the eddy current, means I am using the aluminium frame. So the current carrying conductor near to the aluminium frame means the aluminium frame itself creates the eddy current to oppose the main coil to move. Then it will create actually the damping force to that particular moving system. That's why we are using the aluminium frame. Then the two strong magnetic poles combine to operating the field of the instrument between them. Hence the stray magnetic field cannot much affect to the performance of the instrument. So due to the construction of this instrument, the stray magnetic effect, that is the magnetic field is always same. That's the main thing. These are the main advantages we are using the permanent magnet moving coil instruments. So even though we are having some advantages of the moving coil instrument, we are having some disadvantages also. So because of the sophisticated construction, the instrument cost more than that moving iron instrument. So hereafter we are going to somewhere else we are going to discuss the moving iron instrument. So compared to the moving iron instrument, the moving coil instrument have the much amount of cost. due to that constructional point of view. So because of this presence of the permanent magnet and the springs in the instrument, so we are using the Passport brand's hairspring and also the permanent magnet. The cost of the system may high. Due to that, the error in the reading may arise in the old instrument due to the aging of the magnetic and the spring. So in the permanent magnet, the magnetism actually may lose due to that atmospheric effect. If the temperature of the atmosphere is increases, means we are placing the permanent magnet to the temperature, that is the heat area, the magnetism may lose in the permanent magnet. So if the magnetism loses in the permanent magnet, means it will not show the correct, it will not create correct deflecting torque, and we can create the correct controlling torque, and we can damp the pointer to set the point at the some time. So these are the things happening in the permanent magnet moving coil instruments. Okay. So based on these points, we come to know what is the moving coil instrument and what is the indicating instrument. So indicating instrument is especially for measuring either voltage or a current or the power value. So this is actually the basic mechanism. It is not a meter actually. This is the basic mechanism. From the basic mechanism only, we have to create either it may be a voltmeter or it may be a ammeter. We have to connect the resistance accordingly to create the voltmeter and create the current meter. That is ammeter. Okay, based on it will work. So this is the general arrangement. We can use it for either as a voltmeter, either or as a ammeter. So what sort of amount of resistance I am going to connect, either series or parallel, means I can going to use the voltmeter or as the ammeter. If I connect the resistor to the particular instrument, that instrument I can make it as a ammeter. If I am connecting the resistor in series with this instrument, I can make it as a voltmeter, because the voltage is dividing in the series connection and the current is dividing in the parallel connection. That thing we are already know, I think so. So based on that, we can use the ammeter and voltmeter for the moving coil instrument. Thank you very much for watching. Thank you.